So let's move on to our 10th session of the 6-day FTP. So I invite Dr. Abdul Majid Siti, Assistant Professor, Department of English, Majlis College Autonomous, for the official welcome note. Sir, please.
Hello.
Sir, go on, sir.
Hello.
Yes, sir, you are
Can you
audible.
audible?
Go on.
Can you
Yes,
audible me?
yes, sir.
Yeah.
Yes,
So
sir. Go on.
very good morning to everybody. So good afternoon, good evening to everybody. Venerable Principal, Dr. Momoguti sir, and our guest of honor, Japsir Kheti, dignitaries, and loving and respected delegates, Rapporteur Professor Ajay Kumar, Mr. Chitra PC, technical support, Mr. Akhil sir, well wishes, and my greetings to all of you. We gathered here today as part of FTP program organized by AICTE and Majlis College of Arts and Science. So it gives me great pleasure to welcome you all to today's technical session entitled Waves Forms to Wisdom, ML Techniques for Audio Signal Analysis. This session brings together aspiring researchers, students, and technology enthusiasts to explore one of the most exciting intersections of modern science and machine learning and audio signal processing. We are truly honored to have with us Mr. Japsir Kheti, a leading engineer, data science at Saskins Technology Limited, Chennai. He is a distinguished professional known for his expertise in data science, machine learning engineering, and advanced audio analytics. A strong publication record in concept drift, proven expertise in NLP, computer vision, real-time streaming analytics, passionate about applying ML research to solve complex real-world problems at scale. His work has contributed to innovative solutions in voice recognitions and classification, audio enhancements, and intelligent signal processing systems. So with this strong industry background and deep technical insight, so we are fortunate to have him guide us through the evolving landscape of ML-driven audio analysis. Today's session promises to broaden our understanding of how raw waveforms, symbol a vibration in air, can be transformed into meaningful information through the power of machine learning. So I don't want to go behind the topic. On behalf of these organizers, faculty members, all participants, I extend a warm and hearty welcome to Mr. Japsi sir and all other delegates and those who have come here to participate in this program. So we look forward to an encouraging, an insightful, and inspiring session. Thank you. Thank you once again. Welcome everyone. Thank you. So right now I hand over this session to Mr. Jersey sir for address the gathering. Thank you.
Thank you. Am I audible?
Yes, yes.
Yes, sir. You're
Yes, sir.
audible.
Okay,
Yes, sir.
okay. Yes, I have to share my screen. Can you see the slide?
Yes, sir.
Okay. Thank you. First of all, thank you for giving a wonderful opportunity to speak here. I think in this section, most of the section, we're handling the image, text, and audio, image, mostly image and numerical value and the text. Most of the researchers handling the computer vision programs for the image classification, image segmentation, object detection, like that. I also start my research in machine learning with the image classification, then switch into image segmentation and object detection, etc. Then I switch into streaming data analysis when the IoT devices and the other we need the streaming data analysis. At that time, I changed it to my research into the streaming data analysis, and I completed my research in that field. By the end of my research, that by the arrival of the chat GPT, most of people switch into their research into the NLP, natural language processing. Now most of the people doing some work in the NLP using the LLMs, transformers, etc. But now I came to the another domain. It's the sound, the audio signal. I think audio signal is a starting point of the research. Only 2 or 3 years, most of the people come to the audio signal analysis. I take this topic. The main reason is to take this topic is now I'm handling an audio signal analysis in real time. So we face a lot of challenges for analyzing the audio signals. We know that nowadays the number of opportunities have in the area of the audio signals. In current scenario, we using the audio analysis, speech recognition, voice recognition, etc. And also we use the Google Siri, iOS Siri, Google Assistant, Alexa, etc. All are working the audio signals. So we can switch into our topic. Our topic is from waveform to wisdom. We know the audio signals or sounds are like a waveforms. From waveforms we will arrive into the meaningful insights. That is our topic. These are the agenda. First about what is the why audio and its applications. What is the motivation for the audio analysis? Then what is the audio analysis? Then types of audio data and its representations. Then pre-processing for audio signals for the machine learning, for deep learning and the traditional machine learning also, and model architecture for audio tasks and key tools and libraries. then evaluation metrics and challenges and trends. Why audio signals? We know that audio carries rich temporal and frequency information. It's non-invasive and low cost than the image or videos and easy to capture, and it can use in the environment where camera fails, like we can use if there is no light, especially in the night time, we can use the audios for the authentication, for everything. We know that we have several limitations for the camera, light and its image quality, and we need the higher memory for storing the images and videos, as well as we need the more uh, processor like the GPUs for high-end processors for analyzing the audios. For example, if you use the object detection, for that we need the high-end cameras, and also we need high-end GPU or other processors. And in some places, we cannot use the camera because our privacy issues. In such situation, we can use the audio analysis to identify the persons or authentications. And if someone enter into the room or any place, we can identify by the audio analysis. And also, it's ideal for the real-time monitoring and classification of using the sound. Nowadays, we use the audio analysis in several domains. For example, its applications like the speech and voice. In voice assistants and command recognition like the Siri by Apple and Alexa and Google Assist, we use most of us use this speech and voice recognition, and also we can identify the speaker from their audio. We can identify the speakers. We know that everyone's voice varying in their frequency and amplitudes. We can do that broadly. If you take the frequency of men and women is entirely different, and the amplitude is also different. Wavelength is different, like that. Using this, we can identify who's the speaker, and also we can use the emotion detection from voice. Now, several works going on the emotion detection. If, for example, if someone, we can use it in the customer care field. If someone call you and give the feedback for a feedback of a product or movie, anything, from their voice, we can classify whether it is good or bad. Like at sentiment analysis, previously we did the sentiment analysis using the text, videos, and emojis, everything. But we can analyze the sentiment analysis, even we can detect the emotion from the audio also. And for music intelligence, most of us using the Spotify. Spotify is a better example of using the audio analysis in the music intelligence, and it's classify the music. If you use the Spotify, your home screen is entirely different from others. It's not only based on your search or recent uh, history only, but also they take about the what type of music you hearing and is searching, like that, and the beat tracking, and also um, music recommendations. Spotify mostly using it for the music uh, recommendation. And environmental sound analysis, sirens, phone detections, and also using the wildlife monitoring. We can take the presence of some animals from the sound and using the sound analyzer. Uh, Must have uh, uh, 2 years ago, I got a project for find out the animals in a forest using the camera. At that time, there are several limitations using the camera in the forest, especially in the night time. We cannot use the lights in the forest, and there are several limitations using the camera. For such a situations, we can use the audio analysis for analyzing the presence of a particular animal, and industrial sound monitoring. Currently, I'm working in a project. It detects the quality of the engine for a vehicle, whether it is good or fault. We know that if there is any issue in the engine, mostly its sound may vary. So we can use some sound classification models for detecting whether the engine is good or faulty or uh, good or not okay, etc. And also for the predictive maintenance, I take the example as engine noise because recently I'm working on it. For this, we can find out whether this engine is good or fault, and also we can identify uh, what is the reason for the fault, what is the problem for the engine, like that. And also bearing faults, gear noising, clutch issue, like that, as a automobile domain. And also we can find out the acoustic health. From our voice, we can recognize whether someone is ill or not, is in good health or not, like that. We can identify this using the machines also, using the machine learning model. And in the healthcare and the biomedical domains, we can use the audio or find out the cough, breathe, sound detection. If someone from some people, some ill or the old people stay in the room alone, at that time we can use this method to find out if he or she has any issue, health issue. We can identify using this audio analyzer and heart lung sound analysis and early screening for the respiratory disease. And for security and survival, we can identify the some sounds like the gunshot or glass breaking. If there's no camera, but security is sit in one place at that time, if we hear any sound or glass breaking or gunshot at that time, security will go and search for them. Likewise, we can use some sound analyzer or audio analyzer to find out any uh, any sound like our anomaly detection. We use the anomaly detection in the video. That's like we can use the anomaly detection in audio also, like the gunshot or any glass break, any other uh, uncommon any sounds we can detect, and intrusions alarm using sound and the audio event detection, etc. And the motivation for audio analysis, the audio machine learning enables the proactive insights from the invisible patterns. Uh, Actually, For the use of the machine learning, mostly we can. Okay, sorry. For the use of the machine learning, we always say an use case like, for example, if someone call you any new person, uh, he or she may be friend of your parents. Once they call you, you don't know who is that. At that time, she just recognizes herself that I'm Gita, friend of your mother, like that. Okay, next time if she call you, oh, you you can identify who is calling. But the problem is, how can you explain this? We cannot explain someone's sound, but using the machine learning, we can explain it and we can identify uh, how to who is this. That's a wonderful application of machine learning. And another one is allows continuous monitoring without human supervision. We can continuously monitor using a single microphone and smaller computation footprint. This is the main advantage is the we need only some CPU for analyzing the audio signals. We don't need the high-end machines for like the image or video analysis. These are the motivations, and also it's increasing the demand of the edge-based audio analysis, any mobile devices and edge devices. According to the global market reports, the AI in voice, its demand is increasing. From 2024, it was 3.54 billion. Then now it increased to 4.66 billion. Now they estimate about 13.85 billion in the 2029. It's it's a exponential growth, like when the LLMs and NLP increase after the detection of the transformers. And what is the audio analysis? The audio analysis is we can transform, examine, and interpreting audio signals into extract the meaningful information. We know that audio signal is only a waves. It's like waves like in the water. We can extract the meaningful signals from audio by transforming it into another form. Mostly we capture the audio in the waveform, then we can convert into the spectrogram or any AMFCC like that. From this, we can extract the meaningful information. If we convert into the spectrogram, we can use some deep learning techniques like the image. We can consider it as a image also. And also we can extract the data from MFCC and any other methods, the Chrome like that. And why it matter? It allows machine to hear. We know that we use computer vision as our eyes. We know that AI has several subdomains like machine learning, computer vision, NLP, voice recognition, etc. Mostly, we take the AI model as ourselves, human being. We create a demo or a demo of the human being. So we take how we understand by vision, then we take this logic into the computer vision and how do we learn? That's why learning from the past experience, same logic we use in the machine learning. In the same way, we are learning or we are recognition by here. some noise, the same logic we give into the machine learning to the machines to learn. That's why machine can hear, not only the see. We know we have several use cases currently we are using uh, in the traffic signals, AI cameras, and everything. So there we use the function of our eyes. So the same way we can use the function of our ears by hearing the machines, the audio signals. And we can use in several domains like security, healthcare, entertainment, manufacturing, automotive, everywhere we can use this. And then audio data is represented as the analog. We know that we learned in our BTech or in PG time for the data communications. We know, and also we learn in the 10th standard, the audio signal is the only the analog signals. It flow like a wave like that, and then we have to convert the audio signal to digital form. We know that how to convert the audio signal into the digital form. We use the several methods for the converting the audio signal into the digital form. And for the audio signal, it has mainly three characteristics like time period, amplitude, frequency, and also there is another one is the phase. We stated that's the phase, but the main important thing is the time, amplitude, and frequency. In sometime we need the phase also. Okay, a time period means you know that the audio waves may vary, depends on the sound. Even if I speaking to you, you know that my sound frequency varying, my its amplitude is varying. So always we take the voice based on the time period, okay, and also the amplitude. Amplitude is the intensity of the voice, the loudness. In the simple way, it's the loudness of the voice. We can measure it in the decibels. We know that we can hear. Human being can hear the sound waves frequency from the 20k to the sorry 20 hertz to the 20k hertz. The same way, but in some cases we have to analyze the frequency higher than the 20k, and that's we cannot hear in human being cannot understand. In some places we use only a limited, it is like the up to the 10,000 or up to the 8,000 like that. Okay, you know the difference. What is the difference of the time period, amplitude, and the frequency? Time period is the how many seconds it takes to complete a wave, and amplitude is the its intensity, and frequency is the number of sound waves in a particular time or in a second like that. We know the FFT, fast Fourier transformer. We use the FFT for splitting the frequency. We know there are number of frequencies in each time period. Okay, we have to split each frequency. In sometimes there may be some particular frequency maybe tell you any particular insights from the noise. In such situation, we have to find out each and every frequency. We have to analyze each and every frequencies. Here we can understand the what is the difference between the amplitude, varying the amplitude. If the it's the louder one, in the louder one, its amplitude is higher. If the if is speaking the it's a soft sound, the amplitude will be low. And here in the right side, we can see in a particular time, there are number of frequencies. I just give here the example of three different frequencies, but in a particular second, we have about the 20,000 or the 40,000 or 8,000 frequencies. We have to analyze that. For analyzing the frequency and the decibel, we use the FFT, fast Fourier transformers. We know that what is that. In FFT, it converts the entire signal from time domain. As a human being, we always take the based on the time domain. But from this time domain, there are some insights in the different frequencies, but we can understand that, but we cannot explain what is the difference in the frequencies like that. But using FFT, we can split each and every frequencies and we can analyze it. For FFT, we use the FFT for just converting from the time domain to the frequency domain like this. And our upcoming slides contain only tell about the frequencies, about the FFT, short FFT like that. Then we split from the time domain to the frequency domain and we can analyze each frequencies. Its usage is, if you use the FFT, it gives the global frequency contents and it's good for steady and stationary signals, but FFT, it's not good for the time varying signals. If the audio is the frequently, it's not a varying, it's a steady steady frequency or audio signals, then it's better to use the FFT. And it's not good for the time varying signals like the human speech or engine noise like that. If some cases we have to analyze the steady signals, in such situation, the FFT is better one. And for example, if you use the RPM means if we use our vehicle in a constant RPM, in such situation, if you give the throttle or accelerator, its RPM is constant and we have to find out something from that situation. In such situation, we use the FFTs. But its limitation is that it didn't give any information about the time and we don't know when certain frequency occur. We just know when something happened in the a particular frequency, but we don't know when it's occurred. And you can use only the frequency bins. And another one is the STFT, that is the short time Fourier transformer. What it does, it breaks the signals into small segments. Then it's done what the FFT do, the same thing it will do. But the difference is it splits the entire signal, the audio signals into the segments by the 1 seconds or 2 seconds. Sometimes it may be the milliseconds. Then it analyzes each segment. Then we can understand something happened in a particular time. That's the benefits of the short-time FFT. Using this, we can produce the spectrograms based on the frequency versus the time. In a particular time, which frequencies are present here, like that. And its usage is good for the non-stationary signals. Mostly, we need the SFFT or the STFT rather than the FFT. And we can use it in the speech, music, and the machine noise. In our real-time operation, we use the SFFT for the calculating the loudness or find out the dB. We can find out a particular dB in the particular frequency. In a particular frequency, what is the dB value? We can understand that. And also we can use where the engine acceleration or Mr. anything, some missing. Sometimes there may be some missing in the engine. In such situation, we can use the SFFTs. And the main benefit is it's preserve the time location, time localization, that is the time dependencies, and it reveal the transient events, etc. Mainly, we will get in what frequencies exist at the each moment in that time, and in which frequencies something happens. We can understand using the STFFT. Another one is the real FFT. Is the FFT. We know that the audio signal contain two positive value as well as the negative values. It's cross every time the 0 points, and it will be the positive and negative values. For FFT, it take the both the positive and negative value. Actually, in a wave function, it is the mirror of the one side. But RFFT, it take only the one part. So it's faster and it needs low memory and it will get the same output like that. So it take only the one side. It's neglect the mirrored side. And we can use the now we go to the audio data file formats. We know there are several formats like normally we use the MP3 like that. There are another Wave, AIFE, and FLSC. Everything has its own merits and demerits. But it's better to take the wave file or AIFE for analysis. If you use the wave file, we will get the lossless data. If you use the MP3 or something like that, it may lose some value. It's compress the audio signals to transfer from one media to another media. So it may lose some useful frequencies or useful signals. But if you use the wave files, it's do not remove any useful. It's do not compress. If it compress, it's a lossless compression. And it's just a quick refresh of the sound. We know that sound is the pressure waves. Sometimes it take it as a waves, but it also a pressure wave in some meter like sound level meter. It detects based on its pressure in between the error. If you take if you find out the decibel for a particular frequency or some sound, it's based on the pressure waves. And we know that sound is always analog signals. It's converted into the digital form by sampling, quantization. We know that there are several methods to convert the analog signal into the digital, like the 0-1 format. And also the sample rate. Sample rate is the number of samples per second. That's the hertz, the number of samples in a particular seconds. And with depth and precision of the amplitude and Nyquist theorem. Nyquist theorem is if we want to analyze some frequencies like the 0 to 8,000 or 10,000, definitely you should take the sample rate, the multiple of 2, the double of that frequency. For example, if you want to analyze the entire frequency that human can hear, that is a 20 to 20k hertz, you have to analyze about the 40k. samples. We have to take sample rate as the 40K. That is the Nyquist theorem. And types of audio data and representations. We know that the audio data is in a waveform, it's an analog form. We can represent it in a different form, like the raw waveform, or the raw waveform is just a raw audio signals. Then we can convert it to the spectrogram. Spectrogram is a frequency over time. We can see how to analyze what is the difference between the spectrogram raw form and the MFCC. MFCC is the null frequency. MFCC is the method when how human being understand the audio signal. The same method is used in the MFCC. And also there is the chroma features. That's the tonal class useful in music. It can useful in music. I will show the Python code for how to do this. One minute. I just stop this and share my Python notebook. Can you see this Python notebook? Okay. These are this the waveform. Raw waveform we use for directly in the audio signals. We can use it for the end-to-end deep learning. We know that for deep learning we don't need the extraction of the data like the traditional machine learning. We can use the image and video as a raw. Likewise, we can use the waveforms for the deep learning techniques, for the visualizing the noise and putting out the silent detection for everything, and also for the basic exploratory data analysis. Mainly for a waveform, it may contain number of noises. Okay, we can visualize this. This is the raw waveforms. We can read the audio signals using the librosa. Librosa is the best choice by Python library for the reading and analyzing and feature extraction for the audio analysis. This is an example of raw waveforms. It's a time domain. We can see there is a change in the amplitude. That is a loudness based on the time. There is no information about the frequency, but its shape is very high. I take it only the 18 seconds audio signals, and its shape, you know that its shape is, its size is, how is this, how long it is. And I take the sample rate only the 22,000 because I use here only some the engine noise sound. So it contains maximum the hertz is about the 8,000 something like that. Actually, we need only the 16,000 based on the Nyquist theorem. But here I take the 22 to capture all things, because when I capture this, there was some noises and some howling noises, someone speaking between it, and some other machines sounds, etc. And also there was some blower, the AC blower also. And next one is the STFFT for the spectrogram. For spectrogram, we can use the CNN based the sound classification. Like using the spectrogram, we can use it as take it as a images. Then we can use any classification model, CNN models like the image, and it can use for the noise detection and music analysis and identify the dominant frequencies and harmonic pattern, etc. But the problem is it's large feature matrix, and also it depends on the STFT. STFT means it depends on the time. We can see this is the spectrogram. Here we will get the more data. In waveform, we have only the amplitude and the time domain details. There is no phase or frequency details. But you see the spectrogram, we will get the frequency also. Here it is the time and the frequency also. Here we can see the decimal value. But you just listen that you see the spectrogram, the highest value of the decimal value is the 0. But in real time, it's for about the 0 to 20K or higher. But sorry, it's a dB value. It's dB values like the 50, 100 or 80 or 120 like that. But using the spectrogram, we got only the highest value is the positive one. We have to convert from this value into the original dB value using the equations like the 20 into log of this dB value and plus some kind of constant value. That's us. It's actually it gives the relative value. That's why it's like the minus 80 to the 0. Sometimes it may be the minus 1 to 0 like that. Okay, from here we can identify what is the which is the time in a particular time in a particular frequency. What is the decimal value? Decimal value is based on this color. Like we take the sometimes some confusion. Sorry, we take for it's a varying based on the color only. For higher decibel, it will be the lighter color. For lower decibel, it's the dark color. That's all. And another one is the MFCC. MFCC compress the spectral information to the small number of the coefficients. The model of human audicity and how human understand the audio signals. That is in the MFCC. It's used for the speech recognition and audio classification. If our dataset is very small, it's better to take the MFCC. And feature extraction for the traditional machine learning, SVM, RF, CAT-GOES, or any machine learning classification models. You can use the MFCC. In MFCC, we will get about the 13 values, 13 different values for each time domain. For each samples, we will get that. This is the MFCC details. This is the MFCC coefficient. We can take the values. Mostly, we take the mean of the MFCC values because in a particular second, there may be number of frequencies. At that time, it take only the mean value. And next one is the chroma features. Chroma features always used for music identifications and the music analysis and the tonal similarity and gender classification, etc. but it's not used for the speech or noise recognition. This is the chroma features. These are the different types of features. Okay, we can return to our slide. Okay, these are the four types: waveform, spectrogram, MFCC, and chroma features. These are the comparative study. These are the feature type. It's the representation and which is the best use case, which one is good or not good, like that. Perform always give the amplitude and the time only, and it's best for the signal instructions in the 1D CNN, like that, are not good for the ML models without the pre-processing, because it's only just give you the raw value. If you use the some deep learning model, it's better to use the raw form, and its dimensionality is very high. For the spectrogram, it gives the frequency details, and we can use in the CNN and other machine learning models. And it's not good for the very low tasks, and its dimensionality is high. MFCC is comparatively low frequencies, and chroma. Chroma is very low, but it's used for the music classification or music analysis only. Okay. Why the representation choice matter? We can choose which representation we need. It's only based on our task. That is our use case. We can use it based on that use case. And next is the pre-processing part. We know that what is the audio signals and how it represents. Now, next is pre-processing techniques. If we know that for a machine learning pipeline, we have to collect the data and clean the data, then pre-process and feature extraction. That is a pipeline for the machine learning model. In pre-processing, we have to resample and trimming. Resample means we have to convert from the 16 kilohertz or 22.0 or 44 kilohertz or 8 kilohertz. We have to convert its sample rate. And also trimming means mostly there will be silence in the starting and the ending part of the audio signal. In such situation, we have to trim that silent part. Then we can use. And also sometimes there may be some silent part in between the audio signal. In such situation, we can cancel that noise using the some noise cancellation techniques. Otherwise, in the first step, in the beginning and the end, we can trim, because if we start our mic, there may be some silent parts, and when we stop the mic, there should be a silent part. In such situation, we have to trim that one. Then noise reduction. There may be some noise. This is a very challenging one. If you we can concentrate using a camera. If you go with the image or video, we can concentrate a particular object. But for audio, we cannot concentrate. If you capture the audio signals using some microphone, definitely it contains some noises. If I take the recordings from here. If someone speaking backside or someone singing or any vehicles passed behind the road or any vehicles uh, horn, yeah, everything will capture in the mic. We cannot filter that. So we need the noise reduction techniques or the denoising techniques. And next one is the segmentation. Segmentation means we have to split the audio and their audio signals by the 1 seconds or 2 seconds. In 2 seconds, we will get the pattern of that uh, audio parts. So it's better to take it's based on our use case. Sometimes 1 second or 2 seconds is enough. Sometimes we need the 3 seconds, a maximum 4 or 5 seconds. We will get the entire pattern of that audio signals. And we have to convert into the MEL spectrum, and we will get the MEL spectrum for each chunk, each segment. But in each segment, there may be its sample rate. If its sample rate is 16 or 22K, there may be number of signals, MEL spectra. In such situation, we take the mean of the its MEL spectra. In MEL spectra coefficient, it contains about the 13 values. We have to take relevant. We have to take the meaning of each time segment. And for next step, we have to convert into serial to the mono. We for taking the insights, we convert into the mono. For image, we convert from the color image into the grayscale or the black and white. We convert it to the grayscale. Like that, we have to convert from stereo to mono to analyze the better. Otherwise, it will increase. If the feature set will increase, then we can extract the features, MFCC, spectrogram, chroma, anything. In case of the model architecture, we can use some the traditional models like the RF, CADBOS, SVM, everything, and we can go with the RNN models and or CNN models, then RNN or LSTM because it's a time varying signals. So we can go with the time series data, like we can consider it as a time series data. We can use the RNN, LSTM, any other transformer models also we can use for the recognition. And we can also use the pre-trained models, mostly famous in the YAMNet. YAMNet is the best one for find out. And also we can use the wave-to-wake forms and OpenL3. And there are several uh, pre-trained models available for the audio signals. But the problem is if you use, we can use any pre-trained model like a transfer learning. You can use it for feature extraction or using for the more fine tuning the model, and where you can use that. And tools and libraries. We can consider the audio signal as the just a signal. If we use the wavelets for the signal processing, same way we can consider as a signal, the audio as a signal. We can take the wavelet features from the signals. The most famous method is the Librosa. Librosa is used for the audio or the music analysis. It's a powerful Python library, the Librosa. I can see the Librosa library. And Torch Audio is the another one. Torch Audio is if you use the PyTorch, it's better to use the Torch Audio. And also audio analysis. It also used for the feature extraction, classification, visualization, and OpenSmile and Mosquito. Mosquito, I think I actually Mosquito has a good because if we find out the tonality, sharpness, loudness of a audio, if you use some tools like the a test lab, like the tools, it costs about the 2 lakhs rupees, but we can find out the same details using the mosquito. The problem is mosquito is not matured right now. That may give the wrong results sometime, but we can use after some time because the research is working on it. It will mature within few months. So we can use the mosquito. So last week I used the mosquito, but I couldn't get all the data. I got about the 4 features correctly, but 1 or 2 is I didn't get. So later we can use the mosquito. Even now we can use some useful values like the loudness, sharpness, like that. And we can also use the some pre-trained model for the feature extraction. We just extract the features using the YAML, and we can go with the another CNN model. And evaluation metrics, like all other machine learning for the image and the audio like that, then also use the evaluation metrics based on our task. If it is the classification, we can go to the accuracy, precision, recall, F1 score, everything. And for the speech recognition, we can go with the word error range, and they say like that. The main challenges is on the quality of the record. It fully depends on your mic that used for the recording and environment reference. If you you know that if speaking the mobile phone in a town, it may several noise. We can use some noise cancellation, but the problem is if you use some noise cancellation techniques, it may cancel useful noise also. So it's very difficult to identify. It's very difficult to record the data, very quality data. If you want to train a particular voice, definitely you have to record it in the silence without any other noise in a closed room. You have to record that noise. It's like a human being. If you just someone hear noise records and you try to teach a kid to identify this noise. If it is a single noise, he can identify very quickly. If you, for example, if you record someone's audio from a town or in a traffic jam, there should be number of another noises. So it's difficult to understand. That's like it's very important things to get the quality recorded data. And another is the background noise and ambient sound, everything. There may be if someone goes some noises like the vehicles or the door closing noises, or if you sit in the room, there may be working the fan or air conditions. That blower also gives some noises, and also there may be some noise from outside. Then next one is the lack of labeled data. For image and text data, we have number of labeled data, but for audio signal analysis, there is lack of the labeled data. Next one is the computational complexities and resource needed, but it's less than the compared to the videos. And Next one is the multi-domain model integrations. We can combine it with the audio and with the videos. For example, if we take the object detection, we use only the video, images only. We can also use the audio. We can combine the video and audio. But the problem is, if we combine, there may be some noises. Okay. We know that for our uh, filmmaking, the depth is inside a studio, not in the public, because they want to reduce the noise. That is a thing. And the recent trends and innovations, we use the GPU powered audio processing in real time, and we can use some unified frame rates for the classification, embedding, and also we have the now we're going with the self-supervised learning and everything. And also now mostly we use the audio analysis or video analysis for everything. Transformers, we can use the transformers for that. These are the trends and innovations. Yeah. Now we can just check for the how to take the and the how to extract the features. Okay. Here is a small example of the Python code for feature extraction. Here I used mainly the librosa, and also I used the payload norm, and others are normal, like the NumPy pandas, everything is this. And also we use the PyVT for the wavelet signals. First, we take some the acoustic functions like the compute the loudness. For loudness, I use the pi loudness and loudness, and computing the sharpness, I use the librosa. And for roughness and the fluctuation strength, it's how to fluctuate to the 0, 1, how to cross the 0 like that. And also feature extraction, before feature extraction, we determine which is the SR. SR means the sample rate. I take the 16,000 as the sample rate, and also I take the NFCC is the 13. I take all the 13 MFCC values. We can reduce it. We can take a top 10 or 8 like that. And for here, I just extract the features from the raw audio. I just record the audio signals and take the data from here. That's all. And you take the time domains like the zero crossing time and the root mean square, etc. And the spectral features like the centroid, bandwidth, roll off, fluctuation, etc. And the MFCC data, about the 13 MFCC data, and also the 13 delta MFCC data. Then we take the loudness, sharpness, etc. I just showed. Like the image, we can just record the audio. So just raw audio files as a wave file. It's better to take in the format of wave file than the MP3. Just record the audio in the wave file and store in the format. For example, if the audio signal you can take the data like that. Sorry. Yeah. You take the folder and you take into folder like the faulty or good. And we can label like this. We can label the folder like this and insert all good audios in a particular folder. The name is the good. It's the just a raw audio signals, but it's in the wave format. That's all. And also I take another one in the faulty. Okay. Then we can read like this. Just read the folder and label the data. Just extract the features and label the data. This is the extracted data. We will get the this type. We can get it as a CSV file or Excel sheet. This is the file name. This is the file name. It's segmented data. That's why it's a part one, part two like that. The same audio is a part one, part two, part three like that. And the label also good faulty like that. And zero, zero crossing, RMS, centroid, bandwidth, the role of fluctuation, and the MFCC. MFCC 1 to 30. We can see MFCC 1 to 30 here. Then delta MFCC. Also we can see from 1 to 13 value. Then loudness, sharpness, roughness, and also we can take some tonality using the mosquito and some other features also. Okay, we will get this. From using this data set, we can do any machine learning, traditional machine learning models. And also I will see it is just take a 5 sample of the audio, different audio signals. For example, the class of the faulty, and this is the difference. This is the spectrogram. Here, this head says we take from 0 to 8,000 something because it's an engine noise. It contains only these frequencies. And here we count that its value is 0 to plus 1, the decimal value. Sometimes it may be negative to 0, sometimes maybe the up to 1, 0 to plus 1 like that. These are the samples. The class is a 40. This is a 40. We can find out a particular dB in a particular hertz in a particular time. This is so good. We can see the difference from here, good and faulty. We can see the difference. We can use this image for the CNN to classify. Okay. And also we can find the decimal value, calculate the decimal value. Here I calculate the decimal value. Here the same way I use the LibreSupport reading, and I want to calculate the decimal value in a particular range. At that time, we can take the created band. I like the 1000 to 2000 or the 1000 to 5000 like that. And after that, we can find out. This is the question to find out the dB value. Okay, first we have to find out the FFT in a particular frequency. From that FFT, we can find out dB value using this equation. I told that 20 into log 10 is a particular FFT extracted value plus some relative value, some constant. Here we go to the dB value. The maximum dB in the range is 57.7. In spectrogram, you see that it's from the 0 to plus 1 or negative to plus 1 or 0 like that. From here, we can calculate the dB value like the 57, and here is the 65. and here are the 58 point something, like that. Okay. Any questions?
Thank you, sir. So if the participants has any doubt, you can ask.
Is there anyone doing the research in the audio signal?
Participants can ask doubt. Please unmute and you can ask, or you could ask in the chat box. I hope no one has any doubt. So let's move on.
Is there anyone working on the audio signal? Any research or any other work in the audience? Now, what I think most of the people work in the text on the image, especially the medical image like that. It's okay. If anyone working the audio signals, you can contact me because recently I'm working here. So there are a number of challenges. So just for the identifying and the clarifying that challenges, and you have to resolve that challenges. That's why I'm asking. Okay, thank you.
Thank you very much, sir. So I invite Professor Ajay Kumar, Head of the Department, Computer Science, Majlis College, for the rapport presentation.
Am I audible, sir?
Yeah,
Yes, sir.
audible, sir.
Okay. Thank you, Jesse, sir. Good
Thank
evening
you.
to everyone. Today, we discussed the topic from waveform to wisdom, ML techniques for audio signal analysis. And our resource person is Mr. Jasir Keti, Lead Engineer, Data Science, Sasken Technologies, Chennai. The session focused on how machine learning can be applied to understand and interpret audio signals. The session began with the motivation behind using audio data, highlighting that audio is expensive and non-intrusive. It discussed a wide range of applications, including voice assistance, speech emotion recognition, music genre classification, machine fault diagnosis, healthcare monitoring like cough and breathing sound analysis, and surveillance-based gunshot or glass break detection. We were introduced to the basics of digital audio, time, amplitude, and frequency, and also to common audio file formats. This session then moved into different ways of representing audio for machine learning, such as raw waveforms, spectrograms, MRCCs, and chroma features. He emphasized that choosing the right representation improves models' performance and simplifies learning. Various pre-processing techniques such as resampling, trimming silence, noise reduction, and feature extractions were explained. Also covered machine learning approaches include CNN for spectrogram-based models, RNN, LSTM for sequential audio. Evaluation metrics like accuracy, precision, recall, FN score, and word error rate were briefly discussed. This session concluded with current challenges in audio ML such as quality of record noise, lack of labeled data, and computational complexity. He also demonstrated some samples in Python notebook. It will be very useful for the audience. Overall, this session was insightful, well structured, and provided a clear pathway from the fundamentals of audio signal to modern deep learning based solution. Thank you, Jasir sir.
Thank you.
Thank you very much, Ajay sir. Now, for the official vote of thanks, I invite Ms. Chitara PC, Assistant Professor, Department of Computer Science, Majlis College Autonomous. Ma'am, please.
Hello.
Yeah, ma'am.
Am I
Hi.
audible?
Audible. Yeah,
Yes, ma'am.
audible.
A very good evening to all. I am Chitira, Assistant Professor, Department of Computer Science, Majlis Arts and Science College. I am deeply honored to propose a vote of thanks to for today's 10th technical session on From Waveforms to Wisdom, ML Techniques for Audio Signal Analysis. First of all, I express my sincere gratitude to our respected principal, Dr. Muhammad Kuti, for his guidance and constant support. I extend my heartfelt thanks to today's resource person, Mr. Jafsir Keti, lead engineer in data science, Suscan Technologies Limited, Chennai, for sharing his valuable insights and enriching our knowledge. Thank you, Jafsir sir. I also thank our co-coordinator, Mr. Rafiq, and technical support, Mr. Agil K, for their effort in making this session smooth and successful. A special thanks to our rapporteur, Mr. Ajay Kumar U, and to all faculty members and our participants. Once again, thank you all for being part of this evening session.